Okay, let us pick back up with these notes. The next example is going to be really similar to the one we did with the very last problem, except instead of bears or wolves, this one's moose. So let's go for it. It gives these, the setup says the rate of change of the number of moose, so dm/dt is directly proportional to the 800 minus m, where t is the time in years. It says when time equals 0, there's 100 moose. When time equals 3, there's 500 moose. That's a lot of moose over 3 years, but whatever. All right, dm/dt says that's going to be directly proportional, so k times 800 minus m. Here's all of our work. A is going to take a lot, and then the rest of them going to be really similar, right? Pre-cal stuff there, and then we have the limit question for part D. Okay, so we're going to separate, integrate, do the 20 million steps of algebra, and then we're going to use these two conditions, right? The population of moose at time equals 0 was 100, and then at time equals 3, it was 500. All right, so set up the differential equation, separate, integrate, use the two conditions to solve for the two constants, and then finish all the algebra to get to m equals. A lot of work here for the part A, but the rest of it will be pretty quick once we're done. Okay, so I'm going to go through fairly quickly because this is almost identical to the same example we had last time, except instead of 1200, it's 800. So I'm going to go fairly quick. Divide and separate the integral, the variables. Then we can integrate. Then we would move the negative over and exponentiate. We're also going to drop the absolute value bars also. Because both of those are positive, we can drop them, no worries. So here we've got 800 minus m. There we go. Very much the same as what we did on the last question. And then here, if you wanted to get the n by itself, just add, swap those two. So I have 800 minus c e to the negative kt. Pretty much the same work that we did last time. Now let's go through and let's use the two conditions to solve. So let's use this one first. E to the 0 is 1, so then 800 minus c is 100, therefore the c value is going to have to be 700. And then we can go through and plug it in. And then we could use the second condition to solve for the second constant. Let's do that one over here. Let's use this one. Okay, and then let's do all the algebra. You could solve it with a calculator by graphing and finding the intersection points, or if you got it equal to 0, you could graph and find the x-intercept. Let's just solve it though. So I'm going to add the exponential over, subtract the 500, you divide by 700, you'll have some zeros that cancel, then you would take a natural log, and then you would just need to divide by the negative 3. So here we go. K is going to be negative 1/3 ln of 3/7. Then we would take that, plug it in here. Remember, we had negative k, and since the k value is negative, the two negatives are going to end up canceling, and then we'll get this answer. Finally, all this work for part A, right? Here's the answer all the way to this end. We have 800 minus 700e. The negative from the k and the negative in the k value, those are going to cancel. So it's going to be 1/3 ln of 3/7. If you want to, put all that in parentheses, t. There is our function for this population of moose. A lot of work for it, but hopefully it's okay. Pretty similar to what we did on the last example, nearly identical actually. Just the number here was different, and then the two conditions that it gave us, those were different. But as far as the process and all the work we had to do, pretty much the same. All right, so let me clear off some of this stuff. Let's see if it's going to delete without killing my whole page. There we go. That's enough room, probably. Okay, I want to get rid of that. No, okay, just kidding. No, I won't. All right, so let's do the part B. It says, what's the population going to be at time equals 5? So you just plug in 5. So then you'd have 800 minus 700e to the really ugly number, but then you plug in the 5 for the t-value, and we would end up getting that population is 629 moose. Plural of moose is moose. Kind of weird. Oh well. Part C, so that's done. Actually, let's do part C in different. No, we'll just keep doing it in purple. So part C, we would be finding when it's going to be 700. So we'd set that function equal to 700. Let's see, we got 1/3 ln of 3/7 t. Again, if you had a calculator, which you would, you could use the graphing feature to graph it, find the intersection points. Or if you got it all on the same side so that you had it equal to 0, you could graph and then find the x-intercept. But here I'm just going to solve it. Right? I'm just going to solve it algebraically. So add the exponential over. All right, see you guys. Add the exponential over. Subtract the 700. And then we can solve it. Divide by the 700. Then I would take a natural log. 100 over 700 is just 1/7. So you multiply by 3, and then you could divide by this sucker, ln of 3/7. So that's a pretty ugly t-value. Of course, you would probably just want to type it into the calculator and then get the decimal anyways, which ends up being about 6.89, and then your units for this would be years. So that one would probably look a little bit nicer, but those two things are equivalent. If you wanted the exact solution, we could find it, but if you had a calculator, of course, you could have just used the graphing data calculator and then graphed the both and find the intersection point, and then, or you could have gotten all equal to 0, graphed it, and then found the x-intercept. But we like to be able to do stuff by hand also. Oh, I don't want that. No, go back. I always mess it up. I want the eraser. Okay, so let's try to get rid of some of that stuff. I don't know why it took my function with it. No, okay. Oh, I just got rid of the box around the function. Let's see if I can get rid of that. Okay, it got rid of the box. Okay, Steve, that's fine. Let's just do this last part really quickly before hopefully the announcements come on and rudely interrupt me. Again, it wants us, part D, it wants us to take the limit as t approaches infinity of my population function, of my m function. So here we go, limit as t approaches infinity. Let's go plug that sucker in. So we had 800 minus 700e, and then I had 1/3 ln of 3/7 t. And we want to know what that limit is, right? Kind of this carrying capacity for this model, or that population of moose where that ecosystem is going to trend towards over time. We know the limit of 800 is just 800. That's fine. And then minus 700, but just like before, we're going to need to know, right? The t gets plugged in as infinity, but I need to know whether this number, whether that's a positive decimal or negative decimal, because if it's e to the infinity, you'd have 800 minus 700 times infinity, so you'd have 800 minus infinity, and that wouldn't really make sense. But luckily, remember our natural log graph, it crosses at 1. 3/7 would be before 1. That means this point right here, right, that weird ln, where you have the 1/3 ln of 3/7, that's going to end up being a negative number. So that means, doesn't matter, it's just a weird, ugly decimal. But that means you're going to end up having this minus 700e to the negative infinity. And that's important because the e to the negative infinity is going to make all that chunk go to 0. And so here's our limit, right? Our limit is going to be 800. The units for that would be moose, and that's what your population is going to trend towards over time. Right? As your t-value goes towards infinity, that population is going to head towards 800. Again, that number was in the question the whole time. It was also in your function. Yeah, that example, I know I went quick. The beauty of a video is you can always go back and rewatch it if you need to. But it should have been really similar to the one we did last. Or if you watch the video, it would have been at the end of the last video. Literally everything was the same except some of the numbers, right? It was 800 instead of 1200, your initial value, and then that secondary value, those were different. But as far as the math steps that we took, it was all the same. So I went kind of fast. Hopefully that was okay. You can always go back and rewatch it. I'm probably going to have to pause this video, and then hopefully I can rejoin it. But yeah, I'm going to hop back into the video with the next example here in just a minute. Well, it won't really be any delay for y'all, but there will be a delay for me. Okay, as if by magic, here we go with the next example. Sorry for the interruption. I had to go do a meeting. How exciting. All right, Newton's law of cooling. The rate of change in the temperature of an object is proportional to the difference between the temperature of the object and the temperature of the surrounding medium. That means it's the temperature of that surrounding atmosphere. Let's color code this sucker and we can coordinate what all the different parts mean. The rate of change of the temperature. There's your T, capital T prime, right? Capital T is going to be the temperature. Lowercase t is time. A little bit confusing, but here we have dt, right? Kind of a little bit weird. The rate of change of temperature with respect to time, that is proportional to, so that's k times, and then we have the difference between, so there's our subtraction, difference between the temperature of the object, and then we have the temperature of the surrounding medium. That's like your atmosphere or your environment. And so there's our Newton's law of cooling for us. Let's go through and let's do this first example with it. It says, suppose a room is kept at a constant temperature. So here's my temperature of the medium, right? That's my temperature of that environment, 60 degrees. And a pizza is cooled from 100 degrees to 90 degrees in 10 minutes. That means the temperature at time equals 0 was 100, and the temperature at time equals 10 is 90, right? It kind of gives you those two pieces of information, but you have to think a little bit for them. Part A says find the formula for the temperature. So we're going to have to set it up, separate, integrate, use the two conditions to solve for the C and the K value. Very good. Let's go for it. So the rate of change of the temperature with respect to time, it's going to be K times T minus 60. We're going to separate, so the T minus 60 is going to need to kick over to be with the D capital T, and then the lowercase dt kicks over to the right. Then we could integrate. And here we're going to have ln of T minus 60 is equal to K T plus C. We could exponentiate to get rid of the natural log. Now notice, I didn't need the negative out in front. If you were to do u substitution, right, this would be your u, the derivative of it, let's see, t minus 60, the derivative of that would just be 1 dt, right? So the negative doesn't kick out. If those had been swapped, so if it had been 60 minus t, that's when we would have had the negative, which we then would have needed to move over. But it wasn't swapped. So the variable part was positive. Therefore, I don't need that negative to kick out in front of the log. Right? That one was nice. Be careful when you need that negative. If the subtraction would have been in the reverse direction, we would have, but here we don't. So we integrated, didn't need the negative in front of the log, exponentiated to get rid of the log. Now we're going to think about if we can drop those absolute value bars. Now, for those previous examples where we had population models, it just wouldn't make sense. Like literally, it just doesn't make sense to have a negative population. Is it feasible to have a negative temperature? Yes, right? That's possible. It happens. But in the context of this question, both of the temperatures, really all three of the temperatures that we see, they're all positive. So here, I'm going to be able to drop those absolute value bars. Even though it is possible for temperature to be negative, it is not going to be in this particular context. Then you could just add the 60 over. And I could get the temperature as a function of time. It's going to be C e to the kt plus 60. Or you could switch that because the order doesn't matter for the addition. Now let's use the two conditions to solve. Let's use this first one. So I know the temperature at time equals 0 is 100. Therefore, 100 is going to equal C e k times 0 plus 60. Now, k times 0 is 0. E to the 0 is 1. So really all that is just 1. And so I know my C value is going to be 40. So then we could take that and plug it in. And I know my temperature as a function of time, it's now 40 e to the kt plus 60. And then we can use the second condition to solve for that second constant. So T of 10 is going to be 90. So 90 is going to equal 40 e k times 10. So I'm going to write 10k plus 60. Then here we go. We got 1, 2, 3, 4 things to get rid of in order to get the k by itself. First thing would be to subtract the 60. Then I would divide by 40. I have a 0 that'll cancel. Then I would take a natural log. So I'm going to have ln of 3/4. Once I've taken the natural log, that gets rid of the e. Then I would just need to divide by 10. So there we go. There's our k value. It's 1/10 ln of 3/4. So let's go through, and here we go. We're going to write this final answer, right? Here's all the final answer for A. All this work to get this temperature as a function of time. We had 40 E, plug in the k value. If you want, you can put it in parentheses. 1/10 ln 3/4 T. Not quite. Get rid of there. And then we had, come on, plus 60. So there would be your answer to this part A. A lot of work. Set up the differential equation, separate, integrate, use the two conditions to solve for the two constants. But there we have it, right? That's all the work for the part A. A lot of work, but now we're done. The part B is easy. It just says after how many minutes will the temperature be 80. I'm going to clear this off. I'm going to recopy the function, but I'm going to clear this off. Right. So the answer to part A that we had just done, right? We had temperature as a function of time. We had it was 40 E, and then I had 1/10 ln 3/4 T plus 60. But that was all the answer that we had got from A. I just erased the work so that I can now do the part B. The part B wants me to figure out when is that temperature going to be 80. So I'm going to set that thing equal to 80. Remember, if I had a calculator, I could just graph both of these two things, and I could find the intersection point of them. Or if I want to solve it by hand, I could. You could also get it all on the same side, right? If you move the 80 over, then you could graph that one equation, find the x-intercept, or you could graph both, the left side and the right side, the left side and y1, the right side and y2, or whatever. If you graph both, you find the intersection points. If you get it all on one side so that it's equal to 0, you would graph and find the x-intercept. But I'm going to solve it. Subtract the 60 over. Then I would divide by the 40, which will have some zeros that'll cancel, and then that's going to be a 1/2. Then I would take an ln to get rid of the e. Then I would multiply by 10 to get rid of that. And then I would need to divide. So here we go. I got t is going to be equal 10 ln of 1/2. So that's all the stuff that was over here. And then you would have to divide it by ln of 3/4. And then those ln's don't cancel, those don't reduce at all. That's just the answer, right? That would be an exact solution. Or if you wanted to just type it in and use your calculator, to get to GDC, to get the decimal, that time value would be 24.094 minutes. So just about 24 minutes is slightly longer. That's how long it would take for that temperature to get all the way down to 80. Started at 100, 10 minutes later it was at 90. Looks like it takes about another 14 minutes to drop the extra 10 degrees. All right, so Newton's law of cooling, kind of nice, not super difficult. Sometimes they'll give you this. Sometimes they may even give you the differential equation. But if not, if it only gives us this type of a verbal description, we should still be able to do it. It's proportional to the difference between the temperature of the object minus the temperature of that surrounding medium. Okay, let's move it on to the next example. Here we have it. The population of a certain town increases at a rate that's proportional to the square root of the population. So it's the rate of your population that's proportional to the square root of the population. Okay, I'm going to use the population. I'm going to call that P. Why not? Population, I'm going to call it as P. You don't have to, but I'm going to set it up with P. So the rate of change of the population, that was proportional to the square root of the population. So we set up that differential equation. Very good. Separate. So we're going to have 1 over the root of P, dP, equals K dt. Separate. Then we can integrate. That's going to be 2 roots of P on the left, and then KT plus C. That's just a power rule, right? That integration on the left, that's just a power rule. If you don't know it, it's P to the negative 1/2. So add 1, so you have a positive 1/2. Divide by 1/2 kicks out 2P to the 1/2. So 2 roots of P. Okay, so we've separated, we've integrated. If you want, I can use the conditions right now, right? You don't have to do the algebra. Let's use these conditions right now. It says it goes from 900 to 1604 years. That means the population at time equals 0 was 900, and then the population at time equals 4 is 1600. So let's go use that first one. Let's use this one to solve for one of the constants. So we got P of 0 equals 900, so 2 roots of 900 is going to be equal to K 0 plus C. All right, that's going to be 0. Square root of 900 is 30. 2 times 30 is 60. Okay, so we've got one of them. We can now plug it in. So I've got 2 roots of P is going to be KT plus 60. And then let's use the second one. So I know P of 4 was 1600. So I've got 2 square root of 1600 is equal to K times 4 plus 60. Then we can solve this for K. The square root of 1600 is 40. So 2 times 40, that's 80. 80 minus 60 would be 20. 20 divided by 4 would be 5. So the K value there is 5. So now we can go back and then let's get this answer, right? Here we go. Well, I guess we'll need to come back and finish some of the algebra. So we're going to have 2 roots of P equals the K value. Plug it in as 5, T plus 60, right? Plugging in that K value right here. And then we got to finish the rest of the algebra. So let's see, divide by 2. That's pretty nice. I like the smart board. And then you could square it. So here, if you wanted to, you could have P is equal to, and you could have this whole thing in parentheses, 5T plus 60 over 2 squared. Like, that would be fine. Or if you wanted to, you could rewrite it. P equals, you could have the 1/2 out in front, and then you could have 5T plus 60, and then really all of that would be squared. Or if you wanted to, right, you could square it. You could have 1/4 of 5T plus 60, right? And there's other ways you could write it also. I probably think this is the nicest looking version of it, but any of those previous 2 would have been fine. And you could even have distributed the 1/2, and then you could make it look a little bit different. But I think 5t plus 60 squared and then divided by 4, I think that's probably the best. Okay, so that's all the work. Now we got part A done, and then let's look at the part, let's look at that part B. It says, what will the population be at the end of 10 years? So that just means what is P of 10, right? So that's pretty easy. The part B, I've got enough work. P of 10, we're just going to use our graphing data calculator. Actually, we could probably do this one, right? We got 1/4. 5 times 10 is 50. 50 plus 60 is 110. If I did 110 and then I squared it and then I divided by 4, like that one's not too bad. We probably still would need the calculator, but you could have just plugged it in, right? If you had your function typed into y1, you could just evaluate it. But doing this calculation isn't too bad. We're going to end up getting the population at time equals 10 is 30, 25, and don't forget your units. Be people. And then we're done. Okay, so whether we have those population models of animals or whether we have the population of humans or whether we have a Newton's law of cooling, really all of these differential equations, these applications, if they're buried in the context of a word problem, really they're all kind of those same general steps. Separate, integrate, do all the algebra to get y equals or p equals or b equals or whatever equals. And then at some point in the algebra, either use the condition to solve for C if that's the only thing that's missing, or use the two conditions to solve for both the C and the K if both of them are missing. Right? So long questions, not a whole lot of calculus steps. All right, look at all that stuff. Here's the calculus step, right, which was just integrating. Everything else is just your algebra and your potentially pre-cal skills. Kind of scary, right? Really long questions. And most of it is not going to be the calculus. All right, we've got one more example that we want to get through, and then we'll be done. And here we're probably going to have to, this is a really long question, so I may have to maybe just do the work on the side. We'll see. It's got that, I think the black bar is going to go away when I stop moving it, maybe, I don't know, maybe. I don't think so, actually. That's okay. Let's go for it. It says, this was a question that was on the AP exam a couple years ago, and after my students came back, they were just complaining, oh, the potato question, it was so hard. And I was like, yeah, it wasn't easy, but I taught you how to do it. And so we're going to go through this. It's going to be the last question, and then we'll be done. It says at time equals 0, a boiled potato is taken from a pot on the stove and left to cool in a kitchen. The internal temperature of the potato is 91 degrees Celsius at time equals 0. And then the internal temperature of the potato is greater than 27 degrees for all times. Time is greater than 0. The internal temperature of the potato at time t can be modeled by the function h. Why they're using h for the temperature of the potato, right? Temperature of the potato, that's my variable h. Okay, whatever. That's going to satisfy the differential equation. Okay, so we read this and we're like, okay, see it. I got that differential equation. I've got that initial condition. I'm ready, Mr. Bell. Let me separate. Let me integrate. Let me use that condition to solve for the C value. Bam. It looks easy. Could do it. But it doesn't actually want you to do it. Right? It's kind of weird. That's usually what they're going to have you do for these differential equation type questions when it's a free response, right? Separate, integrate, do all the algebra, use the condition to solve for C. That's a really common free response question. They didn't actually want us to do it here. Let's go read what it wants us to do. Part A, equation for the tangent line at time equals 0, and then we're going to use the tangent line to approximate the temperature at time equals 3. But we've done stuff with tangent lines. Okay, so that's not really new. It was unexpected, but that's not really new. Okay, so let's go for it. We have this graph. I don't know what the graph of h looks like, but it gives us the differential equation. Remember, for the equation of a tangent line, we would want to think about point slope form. And then at that moment that we're investigating, it was time equals 0. Okay, so the temperature at that time, right? The temperature at that time, or I guess I don't need to write it. The temperature at that time is 0 and then 91. So here my x1 value is going to end up being 0. and then my y1 value is going to end up being 91. So I've got y minus 91 equals, I don't know the m yet, and then x minus 0. So I need to somehow find the m, which is the slope, right? Here, this m, where's my part A? M is going to end up being the slope of h at that specific point. So at time equals 3, that means at the point where t, or not time equals 3, it's time equals 0 that we're building everything. Here we go, let's fix it. So at time equals 0. So we know the time at that moment is 0, but then the temperature at that moment is 91. So we kind of know these two facts, right? That's the instant that we're trying to find the tangent line for. We had the y value, plugged it in. We have the x value, the t value. So now we need to get the slope value. But the slope value comes from the derivative. Okay, so there's h prime, right? dh dt, h prime. Let's go take these two values, the 91 and the 0. Let's go plug those in. So h prime, we're going to plug in the 91 as h. If there were any t's, we'd plug them in for 0. Let's look at it. We'd have a negative 1/4. We don't even need the t value. I just need h minus 27. And then 91 minus 27, do a quick little arithmetic. That ends up being 64. And then 64 divided by 4. So the h prime at that moment is going to end up being negative 16. So the negative 16 is the value you would use for the slope of that tangent line. It gave us the point, right? It gave us the point where we're building the tangent line off of. It also already gave me the derivative. So all I had to do was plug that condition in, the h value. All you had to do was plug it in and then get that, hey, the slope at that point is going to end up being 16, negative 16. Okay, so let's see. All this good stuff that we got. I'm going to go ahead and just erase this, right? I'm going to erase it. We're already done with it. We got the equation of that tangent line. I'm going to leave that stuff. Very good. Now let's go ahead and kind of finish the rest of it. What it wants us to do now is we've done this part. Let me switch it. So we've got the equation of the tangent line, but then what it also wanted me to do was approximate the time at 3, right? It wanted me to get an approximation. Hey, what's h of 3? It wants me to use my tangent line to get an approximation for h of 3. Okay, that means I'm going to plug in 3 into the tangent line, and then that corresponding output will be a decent guess for this tangent line. Now, for the part A, this is perfectly good as an answer. But if we're going to have to use the tangent line, it's usually in your best interest to simplify it. So here I've got y equals negative 16x plus 91. So if you were to have done like that extra step, like that's fine, but it would have been okay. Like that's a perfectly good answer. You wouldn't lose any points if you just stopped there, but you have to use that function to now do something. So you would probably want it as y equals for the next step. So we're going to take that new value 3, we're going to plug it in, negative 16 times 3 plus 91, that's negative 48 plus 91. So I know the tangent line's value, right? Y of 3, if I did 91 minus 48, that would be 43. Okay, so the tangent line is equal to 43 degrees Celsius. That means the temperature of the potato at time equals 3, we know it's going to be about 43 degrees Celsius, right? The tangent line is, so it's okay for that to be equals, but the tangent line is just an approximation, right? So the temperature is going to be about 43 degrees. Okay, so that's everything for part A. We did the tangent line, we did the approximation. Cool. We're everything on part A, we're done. Now let's look at the part B. I'm probably going to have to erase all this stuff just to make sure I don't have to keep moving all over the page, but that's okay. You can always rewind the video and then you can look at it if you missed it. And now it's gone. It's gone forever. You can't ever see it again. Well, unless you rewind the video. All right, part B. It says use d squared h dt squared. That's just use h double prime. Use the second derivative to determine whether my answer to part A, so I guess I need to write that, right? We had h of 3, that was about 43 degrees Celsius. right? And we also had the tangent line, whatever. I don't think we need the tangent line, but it was y equals negative 16. T, no, I guess it was x. Let me go back. X, and it was plus 91. So those were the two answers to the part A, right? So we're done. But then part B says use the second derivative to determine if this answer, the 43 degrees, use that to determine if it was an under or an overestimate of that true temperature at time equals 3. Okay, well, if it wants me to use the second derivative, the first thing is I've got to get the second derivative. So let's kind of take this and let's go rewrite it over here. Right, here's all the work for part B. We were given that h prime was negative 1/4 of h minus 27. If you need to distribute, you can, or if you want to just take a derivative, you can just copy the coefficient. The derivative of h is h prime. The derivative of the 27 is 0. So there we have our second derivative. It's just negative 1/4 h prime. And then you probably want to substitute in, right? H prime, plug it in. It was negative 1/4 h minus 27. The two negatives will cancel. So I'm going to get that the second derivative is 1/16 of h minus 27. Right? So there's my formula for the second derivative. Not too bad. And then what we want to do is investigate, was that graph concave up or was that graph concave down? Because the concavity will kind of lead us to knowing whether my estimation was too big or whether it was too small. So let's take that second derivative and let's plug in that moment that we built the tangent line with. Right? So we had time equals 0, and we knew the temperature at that time was 91. Now what's key is you're going back to the point where you used the tangent line. Right? So to the point where we used the tangent line, where we kind of created it, that's the one we're going to check. And we're going to project into that new value with time equals 3. So here we would have 1/16, 91 minus 27. That's 91 minus 27. That's still 64. And so here the second derivative ends up being 4. Okay, and since that is a positive value, right? Since the second derivative was positive, therefore h is going to be concave up. Let me move this. Since the second derivative is positive, h is concave up. So let's think about the graph. We know that. Let me kind of just switch it over. Let me get a different color. Let me go red. Red sticks out pretty easily. We know at that moment the slope was negative. Now I don't really know a whole lot about this graph. Let me just kind of sketch it for us. All right, so we know that point, what was it? It was 0.91. Okay, so that's a pretty big point, right? 0.91. Like there it is. It's up at 91. And we know at that point the slope was pretty steep. So this graph was doing something like this. But we also know the graph was concave up. So it was decreasing, right? We knew the first derivative was negative, and now the second derivative was positive. So it's going to be decreasing but concave up. So it's going to have a shape like this. So more or less, the graph of that potato's temperature is going to look like this. Now our tangent line, this answer that we did on part A, the tangent line hits that function, and then the tangent just keeps going, right? The tangent line ends up keep going with that same slope of negative 16. Whereas since the function is concave up, the function ends up, right, they both intersected, but the function ends up peeling upwards and away from the tangent line. Right? Since it's concave up, the slope of the graph increases, and that ends up above the tangent line, which kind of continues on with that same slope. So here later on, if we were to look at time equals 3, this was the value for the tangent line, right? And we got 43 was the estimate. But since the function was concave up, we know the true function value is going to have to end up being bigger than 43. Right? And the key fact to it was because it was concave up. Because it was concave up, that means the function peels upwards and away from the tangent line, right? The tangent line just keeps going with that same negative 16 slope, but the function, since it's concave up, it ends up higher. So let's go back and let's answer this question. It says, is my answer to part A, is that 43 degrees, is that an overestimate or is it an underestimate? Here, my estimation would have been an underestimate. because my approximation from the tangent line ended up being less than the true function value. The fact that the h was concave up, that was critically important. Okay, so that one was a little bit tricky, right? But we've done stuff with tangent lines. We've done stuff with approximations. We've even talked about over and under. We've seen all stuff like this before. It's just, it was kind of unexpected, right? But yeah, we've seen everything like that before this year. It wasn't what I expected to do on this question, but that's okay. All right, let me clear this, and then let's do part C, and then we be done. Okay, here we go. It says, let me actually, I guess I can leave it. It says, for time is less than 10, an alternate model for this temperature can be given. And it says, okay, forget about H. So that was cool about H. We did all the function H stuff for parts A and B, but now it says, who cares? Now it gives us a different function, dg dt. So now it wants G, right, the temperature of the potato. Now it wants the temperature of that to be G. I don't know why they use H and G for the temperature of a potato. I don't know, who cares? But now it gives us a different model. And here is where it says separate, integrate, use the condition, same condition, use the same condition to solve for the constant, and then get to G equals. I do not know why we never had to separate and integrate that. Right? It would have made sense. It would have been really easy. It gave us the model for H, but we never actually had to integrate that thing. We had to do the tangent line, and then we talked about how the tangent line could have been an over or an under approximation. But we never had to do the calculus for that DHT. We never had to separate, integrate, use the condition, solve for C, and then finish algebra. That would have been a very straightforward question. Stuff like this we've seen how to do. We've seen it like multiple times. You're probably sick of these differential equations by now. But for whatever reason, they didn't want us to do it on that function. They now switch it up. They say, here's G, find, or they give us G prime, and they say, find the expression for G. So here we're going to take dg dt, so dg dt, which was negative G minus 27 to the 2/3 power. So now they give us this, and they want us to separate, integrate, use that condition to solve for the constant. It's the same condition, but they want us to find the G function. And then based on that model, they actually want us to find what the temperature is, right? So they want us to know what is G of 3 going to be. Well, let's separate, integrate, use the condition to solve. So you finish all the algebra, we're going to get the function G, and then we can plug in 3 to it. I don't know why they just didn't have us do that with H. That would have been really nice, but they didn't. Okay, we blame the AP exam graders or writers. Here we go. That chunk with the G minus 27, that's going to have to move over. So G minus 27 to the 2/3, that's going to be on the left with your dg. Then you have just negative or negative 1 dt. Now if you need to, you could rewrite this. That's G minus 27 to the negative 2/3 power, negative 1 dt. Let's do the little bit of u sub work kind of on the side. Right here, your u would be G minus 27. So the du would just be 1 dg. So really the u sub's not going to kick out anything. But I've got this integration of u to the negative 2/3. So if I add 1 to the exponent and then divide by that new number, here's what it's going to end up kicking out as. All right, so when I integrate this left side, it's going to end up integrating 3, and then I have that chunk to the 1/3 power. Okay, that's just a little u sub, a little bit tricky, but that's okay. The integration of negative 1 would be negative t, and then of course we'll put the plus c on that side. And then we want to get the G equals. I would probably right now plug in and solve for the C value. So let's go for it. I knew G of 0 was 91. So I've got 91 minus 27 equals negative 0 plus C. All right, negative 0. See you later. 91 minus 27, that's that same 64 value. Now, the 1/3 power just means cube root. The cube root of 64 is 4. And so here that C value is going to be 12. Okay, so let's go back, plug that 12 in, and then we can finish all the algebra. Here we go. That C value, let's plug it in as 12. And then we can finish the rest of this algebra to get this question all the way done. I'm going to just kind of clear this so I have room to finish the algebra, right? Using the condition to solve for C, but now all that work, it doesn't matter, right? Because we're already done with it. Okay, so now let's continue on. I would want to divide by 3. So I have G minus 27 and the cube root of it. I'm going to actually write this. Instead of negative T plus 12, I'm going to rewrite that as just 12 minus T. I'm just going to put it all over 3. And then to undo the cube root, you would cube both sides, right? So here, if I cube both sides, that would cancel, and then you just have to add the 27. So here is my G function. It's going to end up being 12 minus T over 3 cubed, and then plus 27. Right, there's the G equation. I don't know why I use black, because we have that black bar in the middle. Oh well, there we go. I'll put the box with red. There's the G equation. And then the last thing it wanted me to do was to come back, and we wanted to find what G of 3 is. So I'm just going to take 3, plug it in, and then we can go for it. So here we're going to have 12 minus 3 over 3 cubed plus 27, and then we can figure out what G of 3, the exact temperature this function tells us is going to be. 12 minus 3 is 9. 9 divided by 3 is 3. 3 cubed is 27. 27 plus 27 is 54. So that true function value ended up being 54 degrees Celsius. Okay, so this was a pretty nice question. It was kind of unanticipated, right? We're done with everything here. We found the G, then we approximated it. Very good. Always make sure you answer every single part. But that one was a little bit weird. It gave us the function for h prime, and I was expecting, the first time I saw this, I was expecting to have to separate and integrate that guy. Now, we never needed to do that. We just did the tangent line and the approximation, and we determined that it was an under approximation. We did tangent line stuff based on h. But then it gave us a curveball. It switched it to this function g, and it says, okay, well, g is what we're going to end up integrating. Okay, well, I don't know why it switched it, but we're able to integrate either of those. The fact that it switched it and that we had to do everything with g, yeah, that was annoying, but not the end of the world. We know how to use tangent lines. We should be able to determine if it was under or over. We also know how to separate, integrate, and use the condition to solve for C, right? The differential equation stuff was really in this part C. The parts A and B, that was all just tangent line stuff that we've done in the past. So hard question, yeah. Is it a question that every single one of my students should have been belly aching about? No, because you were taught how to do every single part of it. It was just a little bit weird. Why do they use H for the potato or G? Who knows? But that's not our job to question the question. We just answer the question. And every part of that is something that you should have known how to do. Because I taught you every single thing on that question. I taught you how to do. It's just whether you put in the practice and whether you can remember how to do it. And that's how the rest of your AP exam is going to be. I promise you, every single thing you see on the test, I would have taught you how to do. It's just whether or not you put in the work to remember it, to get it committed into your brain, or if you just kind of skimmed through it and then you forgot everything, which would be sad. All right, but that's it. That's the end of our little applications. The next video, we're going to talk about slope fields, which are going to be a little bit annoying, but pretty easy to do.